The process to locate the epileptogenic zone starts with the stereotactic electroencephalography, the so-called SEEG, that records neural activity directly in the brain. Comparing the empirical brain signals to a range of simulations can narrow down the potentially affected regions of the brain. The current state-of-the-art model is the virtual brain. It's a personalised computational model where brain regions are reduced to point-like nodes in a network, discarding their orientations. A mathematical model is attached to each node. Additionally, the brain's complex connectivity is derived from the patient's MR images. In the virtual brain, the neural activity recorded by the SEEG electrodes is expressed as a function of the distance to the point sources of the network. While this approach helps to narrow down the affected regions, the low spatial resolution and loss of orientation of the neural sources limits the precision in identifying the epileptogenic zone. In e-brains, more powerful computers and the integration of highly heterogeneous data enables a new approach, the virtual big brain. Some of the data comes directly from the patient, and some is high-resolution data from post-mortem brains. But instead of reducing the brain regions to a network of point-like nodes, we can create high-resolution surfaces for the cortex and subcortex. The brain's multi-scale connectivity is integrated into a high-resolution mesh of more than 200,000 vertices spanned in 3 dimensions. All the vertices of the mesh are equipped with mathematical models of neuronal populations. Intracortical fibres, short-range U fibres, and long-range corticocortical fibres connect neuronal populations in the same mesh. The model is supplemented by dipole moments. They are mimicking the alignment of the pyramidal neurons, which are also perpendicular to the surface. The SEEG can now be simulated using distance and orientation of the sources. This was not possible before. The simulated activities are not constrained to network nodes anymore. They can propagate across the brain surface. Researchers can simulate countless epileptic seizures in e-brains using the virtual big brain. The application of deep learning and Bayesian inference finds the parameter configuration that most closely matches the patient's own SEEG recordings. This is an important step towards pinpointing the epileptogenic zone with greater precision.